তো স্বাগতম সবাইকে আমাদের আজকের ওয়েবিনারে। সো আমাদের আজকের ওয়েবিনার হচ্ছে ড্রোন বেসড রিমোট লাইভ সেন্সিং রাডার ফর সার্চ এন্ড রেস্কিউ অপারেশন অ্যাপ্লিকেশনস। সো মূলত বাংলাদেশ ফ্লাইং ল্যাবসের পক্ষ থেকে এই ওয়েবিনারটা অর্গানাইজ করা হচ্ছে এবং আমাদের আজকের স্পিকার হচ্ছেন ডাক্তার শাহেক মাহমুদুল ইসলাম। সো স্যার হচ্ছেন ঢাকা ইউনিভার্সিটি ইলেকট্রনিক্স এন্ড ইলেকট্রিক্যাল এন্ড ইঞ্জিনিয়ারিং ডিপার্টমেন্টের একজন লেকচারার। বিএসসি এবং এমএসসি কমপ্লিট করেছেন ঢাকা ইউনিভার্সিটি একই ডিপার্টমেন্ট থেকে এবং পিএইচডি করেছেন ইউনিভার্সিটি ওয়াই মাওয়ানাতে ইউএসএ থেকে। তো আমরা সবাই হয়তো আপনারা যারা জয়েন করেছেন স্যারের বায়োটা অবশ্যই আপনারা পড়েছেন আমরা আশা করছি। সো আমরা হচ্ছে আজকের এই ওয়েবিনার শুরু করার আগে আমরা সবাই জানি, তবে জিনিসগুলো একটু আমাদের কাছে জাস্ট রিমাইন্ড করে দেওয়া। জুমের যে বেসিক জিনিস, আমরা যদি কখন কথা না বলি, আমরা যখন ওয়েবিনারটা শুনবো বা যখন পার্টিসিপেট করবো, আশা করি আমাদের মাইক্রোফোনটা আমরা মিউট করে রাখবো যদি কোনো প্রয়োজন না থাকে। যদি সম্ভব হয় আমাদের ভিডিও ক্যামেরাটা অন করে রাখবো, তাতে হচ্ছে ইন্টারাকশনটা ভালো হয় এবং যিনি ইয়া করছেন তার জন্য অনেক ইফেক্টিভ হয় আর কি। সো এই জন্য আমরা চেষ্টা করবো যদি কোনো সমস্যা না থাকে আমাদের ভিডিও ক্যামেরাটা আমরা অন করে রাখবো। আমাদের চ্যাট অপশনটা আমরা ইউজ করবো যদি আমাদের কোনো কোশ্চেন থাকে সেই কোশ্চেন আস্ক করার জন্য, অথবা যদি কোনো ইয়া থাকে আমরা রিয়াকশন জানাতে চাই সেই ক্ষেত্রে। আর যদি ওয়েবিনার চলাকালীন সময়ে আমাদের কোনো কোশ্চেন থাকে আমরা হ্যান্ড রেজ করতে পারি। ওয়েবিনারের শেষে যখন কোশ্চেন আনসার সেশন থাকবে তখন স্যার চেষ্টা করবেন আপনাদের কোশ্চেনগুলোকে অ্যান্সার করার জন্য। এবং এখানে একটা গুরুত্বপূর্ণ বিষয় যে আমরা হচ্ছে পুরো যে সেশনটা ওয়েবিনারটা আমরা রেকর্ড করব এবং রেকর্ডগুলো পরবর্তীতে আমাদের যে সোশ্যাল মিডিয়া প্ল্যাটফর্মগুলো আছে সেগুলোতে পাবলিশ করা হবে। সো এই ক্ষেত্রে আমরা আপনাদের কনসেপ্ট নিয়ে নিতে চাচ্ছি এখনই যে আমরা এই রেকর্ডিংটা পরবর্তীতে আমাদের সোশ্যাল মিডিয়া প্ল্যাটফর্মগুলোতে পাবলিশ করা হবে। সো এখন আমরা একটু বাংলাদেশ ফ্লাইং ল্যাবস নিয়ে বলি যে বাংলাদেশ ফ্লাইং ল্যাবস হচ্ছে একটা সোশ্যাল হাব, যে সোশ্যাল হাবটা হচ্ছে রোবোটিক্স, ড্রোন বা এই ইমার্জিং টেকনোলজি গুলো নিয়ে ইনথুজিয়াস্ট যারা তাদেরকে নিয়ে কাজ করে। মূলত হচ্ছে এই ইনথুজিয়াস্টদেরকে সোশ্যালি প্রমোট করা, তাদেরকে কাজে অগ্রসর করে দেওয়া এবং ইন্টারন্যাশনাল এবং লোকাল কমিউনিটির মধ্যে একটা ব্রিজ তৈরি করা, এটাই হচ্ছে আমাদের বাংলাদেশ ফ্লাইং ল্যাবস এর মটো। সো নিউ জেনারেশনকে ইমার্জিং টেকনোলজি গুলোর সঙ্গে পরিচয় করিয়ে দেওয়ার জন্য বাংলাদেশ ফ্লাইং ল্যাবস ইন্টারন্যাশনাল এবং লোকাল হাবগুলোর সঙ্গে একটা ব্রিজ তৈরি করার কাজ করে থাকে। সো আমি এখন এই মুহূর্তে রিকোয়েস্ট করবো স্যারকে, যদি স্যার আমাদের এই যে ওয়েবিনারটা সেটা শুরু করেন।
ঠিক আছে, আমি শুরু করতে চাচ্ছি। আচ্ছা, শেয়ার স্ক্রিন। আচ্ছা, আমার স্ক্রিন দেখা যাচ্ছে?
জি স্যার, দেখা যাচ্ছে।
আচ্ছা, আমার কথা তো শোনা যাচ্ছে, তাই না?
জি।
আচ্ছা, তো এটা তো ইংলিশে কন্ডাক্ট করার কথা, আমি ইংলিশে তাহলে পুরোটা কন্ডাক্ট করতেছি, তাতে সমস্যা নেই না? বাংলায় বলা লাগবে?
জি স্যার।
আচ্ছা, ওকে ওকে। সো thank you for providing me this opportunity. So it's absolutely my pleasure to talk about some of the new emerging area of a drone-based remote live sensing technology for search and rescue applications. So the basic idea, basically, I divided my talk in like 4 different segments. First, I would like to talk about like how Doppler radar-based non-contact monitoring technique works and the basic principles of it. Then I will try to talk about like what are the potential application areas of this biomedical radar technology. And I'll try to cover like a broader spectrum of this biomedical radar sensing technology. And then I will also talk about like what are the recent progresses of this remote live sensing radar technology. And here I should mention that like this technology is not that much matured, so there are a lot of scopes to work. So there are a lot of rooms, I should say. So it's a good news for all of us because we can work and we can collaborate, we can publish, and we can like basically try to push this technology to bring into real life. And then I will also talk about like what are the research challenges for implementing this sensor technology. And then I'll try to show some future potential areas and what this particular technology can do. So initially I would start with like what is drone and how drone works, or what is drone. So basically we all are familiar what is drone. It's a small size remote control device and it works without any pilot, or it's kind of like a driverless system. So here drone can be classified basically 2 different areas. One is called like multi-rotor drone, another is called like fixed wing drone. So here you can see it's a multi-rotor drone and it's very smaller and cheaper. And so we can like use this type of drone for photography and other things. It's like a very popular nowadays. So what are the typical applications of drone? If we look at the typical applications of drone, basically we know that it's basically used for like surveying or mapping, like Google Maps and other thing where drone is being used. Then another recent like application is like a Amazon food delivery service. I also use this service quite a lot of time when I was in US. And then for our country, like smart irrigation system using drone can be one of the potential solutions for our agriculture sector. So I think we all are familiar with this type of typical applications of drone, but today I'm going to talk about like little bit different areas. And I think like most of are not that much familiar with this concept. It's called like indoor drone-based radar restoration concept. So let's have a look. Like let's say someone is trapped or injured after some post-disaster scenarios. Like it may be earthquake, it may be fire incidents or anything. And let's say this particular guy is like injured, or he or she may like may have some life, but we want to like track this person. So what we can do, like we can expect like that fast responder will go and try to rescue the particular person. But the problem is that due to the harsh environment, fast responders cannot go there like very fast, and at the same time they cannot rescue people like quite easily. So what we can do, we can send drone. As we said, like drone has one of the potential advantages of is like mobility. It can move like different places without any like driver or any pilot. That's one of the potential benefits. And we also know that drone mounted with camera is like a very popular, as it's being used by Google Map and other things. So, but for this particular scenario, let's say this particular person is breathing, but drone with camera cannot like detect this particular person because due to the harsh environment. At the same time, you know that camera cannot pass through wall and other things. However, if we replace this particular camera with a radar, basically it can send electromagnetic signal towards the towards human, and when the signal is being reflected from there, we can like extract some important physiological information like breathing rate and heart rate. And I will talk about in details like how this particular technology works in my later slides. And this kind of particular technology can be helpful for search and rescue application. And it can easily supersede the existing technology like the camera mounted with drone, because camera, I already told you that camera cannot pass through wall, camera cannot work without like optimal light condition or without optimal light intensity, whereas drone is kind of like drone with mounted with radar is basically a solution where it can pass through wall, it can pass through any kind of fog, fire, or any kind of incidents. And I'll talk about like how this technology works and what are the basic principles. So here, I think you are a little bit familiar with radar. Radar is basically a transceiver. I think you all know that you have a Wi-Fi router in your home. So Wi-Fi router is a kind of like a transmitter. It sends a signal, and the cell phone we are using is a receiver. On the other hand, radar is basically, it contains both transmitter and receiver. And so radar in short is called like radio detection and ranging. So here I'm trying to show like how radar detect a target. So let's say this particular car is moving with a velocity vt. So when the signal is sent with a frequency f, and after when it strikes that particular target, basically its frequency changes or frequency shift occurs. That we all know, that's called like a Doppler shift. And from this frequency shift, basically we can know about this velocity of the target. At the same time, we can find like position of the target and other things. A lot of things can be done. Tracking and other things is possible. So for physiological sensing, that's what is our target and how radar can do that. So here, what happens is like when radar sends an electromagnetic signal towards a human, basically due to cardiorespiratory activities, chest surface moves occurs. So when signal is being reflected from the chest surface, basically its phase change occurs. You can see here there is the phase change between the transmitter signal and the reflector signal. And I'm trying to show here transmitter signal with a like violet color and dotted line as a receive signal. So easily it can show that this phase change is directly proportional to the tiny movement of the chest surface due to the cardiorespiratory activities. And if we can track this phase change information, basically we can extract a lot of vital signs information such as breathing rate, heart rate, tidal volume, and other valuable information. And that can be also used for search and rescue applications. So the question may come, like apart from the physiological movement, like apart from the tiny movement of the chest surface, there may be some other clutters, like some other object which is not moving. So we can also remove that part and we can just focus on this periodic part and we can extract some vital sign information. I'll talk about in details in my later slides how to do that. So here I'm trying to show, as I said, that radar is basically a transceiver. So it has an antenna, and then same antenna can be also used for reception of the signal. And when the signal is being received, basically it's again multiplied with the transmitter signal using RF signal generator. And from there, we can get two channel signal. One is called like in-phase channel, another is called like quadrature version, like the 90-degree phase shifted version of that particular reflected signal. And then all radar, like you can buy different radar module, all radar have a DAC, data acquisition system. And from there, we can do a lot of signal processing using MATLAB and other like Python and other toolbox you can use. So here you can see here basically the chest displacement is occurring like xt. I'm representing that as a chest displacement that is occurring due to the cardiorespiratory activities like the breathing rate and heart rate information is there. And from D naught is basically I'm representing that from the displacement from the chest surface towards the transmitter antenna. And we can, when there is a moving target, basically phase change occurs, as I already mentioned that. And if there is a stationary target, basically this phase change doesn't occur. And from there, we can understand like whether there is a movement of the object or subject or not. So this can be easily discerned through that particular phase information. And cardiorespiratory motions and rates can be extracted, as I mentioned, from the phase variations. And from this particular variation, basically, we can do a lot of stuff. We can do like, we can recognize the people's different activities. We can find whether there is a participants. We can find like whether there is any kind of respiratory disorder. So it's like basically a multifunctional activities we can basically extract. And now, as I mentioned, I will try to discuss this basic principle with some simple equations so that it again becomes clear. So let's say, as I mentioned, the basic idea of this technique is like the phase change of the reflected signal is directly proportional to the tiny movement of the chest surface due to the cardiorespiratory activities. And this cardiorespiratory activities is occurring due to the breathing rate and heart rate related information or due to the movement of our heart. So when signal is being transmitted, let's say I'm representing this signal as a T, where A is the amplitude, F is the frequency of the signal, and phi t is the phase of the signal. And when the signal is being reflected due to the tiny movement of the chest surface, you can see its phase change occurs. So that particular phase change, this experiment we did in a like anechoic chamber where we put the participants in front of the radar, and then in a single subject measurement, basically when, as I mentioned, when the signal is being reflected, basically, if it is a quadrature radar, we can get two different channel signal. One is called in-phase channel signal, and another is called quadrature phase shifted version of the signal. And here you can see it's represented as BIT, where A is basically the amplitude, D naught is the distance from the chest towards the antenna, and XT is basically the chest displacement, and del phi t is basically the phase noise of this RF signal generator, and that can be easily deducted from the equation and also from the signal. And similarly, we can get the same signal from the quadrature, but it's basically the phase shifted version of the transmitter signal. And from these two channel signals, whenever we receive these two channel signals, let's say we have a I channel signal, we have a Q channel signal, and now we can draw basically IQ plot, and it's called like a constellation diagram. So let's say here y-axis is Q and x-axis is I. If we draw this IQ plot, basically we can get a quadrature. It forms basically an arc, and from their arc, basically we can also extract the radius of the arc. And if it is a periodic motion, basically it will form an arc. If it is not a periodic motion, it will not form an arc, and it will not maintain a constant radius. So that's the good news. Like in that way, basically we can discern between whether there is a movement or whether there is not a periodic movement. So this particular movement can be deducted. And then from here, we can also extract the center of this particular arc, and we can also extract the radius of the arc. And that gives us the information called ERCS, effective radar cross section. So that basically determines like how much energy is being absorbed by that particular surface or that particular target. So as I mentioned, when there is a periodic motion, there will be a fixed point, and IQ plot, you can see an arc. And if there is a sedentary respiration, let's say someone is breathing like normal breathing pattern, then we can get a constant radius. But if there is any kind of fluctuating radius, let's say someone is walking or someone is like waving his hand or arms, then his radius would change. And that can easily like help us to discern that this is not coming from the breathing. And so if there is a breathing information, basically it will form an arc. And if there is not breathing related information, there may be a walking or there may be a hand waving or other thing, then it will not be a constant radius arc. So in that way, we can understand like which portion of the signal carries the valuable information, especially the vital signs. So as I mentioned now, we got two channel signals, IQ, and from two channel signal, we can do IQ plot. At the same time, we can get the maximum chest displacement information by doing the demodulation. There are two different types of demodulation is being used. One is called the principal component analysis or linear demodulation. Another one is called like arc engine demodulation. So linear demodulation is basically, I think those who are familiar with the signal processing is called PCA, principal component analysis, which tries to find the maximum chest displacement information or the maximum displacement information or dispersion direction from the two channel signal. And from there, we can get the maximum chest displacement information. And similarly, we can also use the arc engine demodulation of these two channel signals, which basically helps us to extract the angle information from two channel signals. And once we got the best amplitude signal or the best chest displacement information, from there we can take the FFT of the fast Fourier transform of that signal, which tells us about the breathing rate information. So if it is like a sedentary condition, generally, you know that 12 to 20 beats per minute, which is basically 0.2 to 0.5 hertz. In between, we can get the breathing rate. And for extracting heart rate, basically we need to use another bandpass filter, which lies in between the 0.8 to 0.2 hertz, which can help us also extract the another vital sign information is heart rate. So from the captured radar signal, basically we can extract all this vital sign information, not only the breathing rate and heart rate. We can also find other respiratory features like the chest displacement information, tidal volume, heart rate variability, and a lot of stuff we can extract. So another question may come, like as we are using the electromagnetic wave. So let's say here you can get that if someone is like waving his hand or someone is moving his limb. So you can see this portion is coming from the limb motion and this portion is coming from the breathing. So what we can do, we can basically do the periodicity test and we can remove this limb motion part and we can just focus on the periodic part, and then we can do the bandpass filtering and FFT to extract the breathing rate and heart rate related information. So in that way, basically, if there is other person walking and other person doing other activities, that can be easily like discriminated from the captured signal, and we can just extract the vital signs related information, like the breathing rate and heart rate related information. So as I mentioned, first in my talk, I am trying to focus or I'm trying to discuss like as much the broader spectrum of radar technology, especially for the biomedical applications. Then I'll try to discuss like how this technology can be integrated with the drone and what are the like recent progress of this technology. So here you can see one of the benefit of this technique is like it is a non-contact technique, it's a non-invasive technique, it's an unobtrusive technique, and this particular sensing technology can go through clothing, wall, and non-contact. So a lot of advantages than the traditional sensing method. So sedentary rates can also measure. We did this experiment in my university where I did my PhD. So here what we did, like we put the radar system and then we put some participants in a seated position where participants up to like 1 meter to 100 meter using different radar power, we can extract like their breathing rate and heart rate information. So easily we can use this technique for remote sensing. So it's like 100 meter is like a lot of range. Still we are using like a short range radar, but we can extract the vital signs reliably, and it shows like a very good cross correlation with the chest belt extractor signals. So some of the potential health related application areas, such as like as I mentioned, it can be used for recognition of different sedentary and activities. Here I am trying to show the first FDA approved device where radar is used, and it can detect the breathing rate and heart rate related information. And then for any kind of like sleep disorder, that sleep apnea, when people's breathing pattern stops, that can also be extracted through radar. And we can also measure the tidal volume of like different participants' tidal volume information, like when people try to breathe, like their breathing respiratory related information can also be extracted. And recently we also worked on like recognizing different postures, like let's say someone is sleeping on their back, someone is sleeping on their side, and from the ERCS or from the I talked about like IQ channel signal, and you see when people are sitting on their, or when people are sleeping on their back, basically its radius is different. You see, when people are sleeping on their side, its radius is also different. So in that way, from the radius or from the ERCS, effective radar cross section, basically we can recognize different sleep postures. So which helps us to comment about our sleep quality, and at the same time, it can also be used for non-contact sleep medicine. So all these are like some of the amazing applications of radar technology. And then another very like one of the potential application is like obstructive sleep apnea, as I mentioned before. So we did some clinical study with the Queen's Medical Center. So what we did, basically, you see the radar system we integrated with the traditional gold standard system. So what happens, I think, if you are not familiar with sleep apnea, so when people have a sleep apnea, basically when people sleep, their breathing pattern stops, and breathing pattern stops like for more than 10 seconds. So which is a kind of scary, and it can any time, like their sleep pattern and other thing, their sleep quality is a little bit different than the normal sleeping pattern. So what happens, like if someone is suffering from this OSA, obstructive sleep apnea, he or she needs to go to sleep study center, where it's a kind of like cumbersome process where he needs to wear all different kinds of contact sensors, and then he needs to do this type of testing in a dedicated lab. But we are proposing like this radar sensor technology, where patients don't need to wear anything. You can see we put this particular sensor system in front of the patient, and we basically try to see like how much accurate our system was with the like the gold standard system, which is called like polysomnography, PSG. And as I mentioned, we also did the sleep posture recognition system, like when people sleep on their side or sleep on their back. If you look at their IQ plot, from that IQ plot, if you try to find the radius of the arc, in that way, you can see there is a very lot more differences in their radiuses, and in that way we can like recognize different postures. So here you can see from the respiratory rate, if we do this type of monitoring, we can find like apnea, hyperapnea, and different events. Another project I worked on, and another important area like people are working on, is called unique identification, and that's what I did my PhD on, this particular topic, like recognizing people from their respiratory pattern. So radar is basically capturing the tiny movement of the chest surface, and we are proposing that fingerprint is basically the traditional authentication system. So if we can replace the traditional authentication system with some respiratory pattern, whether like recognizing people from their breathing diversity, is it possible or not? That's what I try to investigate in my PhD thesis. So there's another area people are working, it's a new and emerging area. So again, I would say like for obstructive sleep apnea, you can see when people are taking normal respiration, there is a tract with no phase variation between thorax and abdomen. You can see, like say participant is taking normal, there is no variation in their thorax and abdomen, and there is no phase variation. So if we draw this plot from the radar signal, it would have a constant radius and it would have a fixed IQ plot. And then if there is any kind of like respiratory disorder, like that I talked about obstructive sleep apnea, and if there is any kind of paradoxical respiration, you can see here in the abdomen and thorax, there is a out of sync and there is a phase variation, which can easily be tracked by the radar signal. And in that way, basically, we can find different respiratory disorder. At the same time, we can extract like the respiratory related disorder information. So we can do the screening of the obstructive sleep apnea easily using the radar technology. So here, I try to show here, as I mentioned, if someone goes to dedicated sleep study center for doing this type of obstructive sleep apnea, that's called a PSG. It's called like a polysomnography. In the polysomnography, you can see here there are more than like 10 sensors are used, and all of them are contact sensors. So you can imagine like how much like terrific it can be, or how much like hard working it would be if you go to this type of sleep study center, where patients need to wear all this type of sensor, and then he needs to go for sleep. So basically all this contact sensor is going to like hamper his or her sleep study, his or her sleep pattern. And you can see this is one of the results of the sleep results. They try to find like muscle pressure, airflow, chest displacement, abdomen, and a lot of things they try to extract. But if we can have a radar, basically they don't need to wire all this type of sensor, and radar can track the respiratory related disorder. And if we can use this sensor system as a pre-screening technique in an in-home environment, and then once the patient is diagnosed by radar, if they take this type of test, I think that would be much more feasible, especially for those who don't have that much money. Because if you go this type of sleep study center, it's like almost like $1,000 and more than that. I don't know about the cost for Bangladesh, but I know about the cost for US is almost like 1,000 USD. So all this technique we try to propose, and we did this experiment with the Queen's Medical Center, and we already published a paper. You can see this paper in IEEE sensor, and we try to show here I'm trying to show that you see the respiratory trace with the time and amplitude, and then we try to find the respiratory rate, and we also trying to find then how is the phase delay between the chest and abdomen. As I said, when there is a respiratory disorder, there will be delay between the abdomen and thorax, and in that way we can extract whether there is a respiratory related disorder or not. So that helps us to discriminate or to discern between the normal breathing or other abnormal breathing pattern. So another thing as I mentioned, another thing work on sleep posture recognition using radar is getting attention, and a lot of people are working is a non-contact sleep posture recognition. So we did that study for 20 subjects. And you can see using the RCS, radar cross-section, as I say, you see the two sleep postures. One is called supine, another is a prone. And if you look at ERCS here, the radius is different. And based on that radius, we can say which one is sleeping in what type of positions. So posture recognition is possible, which is one of the good things. That sometimes for sudden infant death syndrome, many child, they becomes dead just because of the sleep posture. So we can also use this technology for other aspects of this, sudden infant death syndrome and other related diseases, which is kind of respiratory related disorders. So now I'll try to cover what are the potential application areas of this biomedical Doppler radar, and I try to cover the broader spectrum of this technology. Now I will just focus on what have been done using drone-based radar for search and rescue application. Now from my previous slides, I think most of you got the idea. When radar is being used, from that radar signal, we can capture the tiny movement of the chest surface, and we can get the some vital signs information, like the breathing rate and heart rate related information. So UAV-borne radar, if you look at this terminology in a Google, you can see it's not that much mature technology. I think people started working on this technology from probably 2015, so it's not that much mature technology. Still people are investigating, and I'll show you what has been done and what are the challenges and what we can do. As it is not a mature technology, so which is a good thing for us, those who are listening. Basically, we can work on this particular area, and we can try to push this area to bring into our day-to-day life. So for UAV-borne radar, what we need to do, basically, we need to mount this radar with the drone, and there are two ways to use this radar. One is called Doppler mode. So you can see here a drone is mounted, a radar is mounted with drone, and it tries to fly over that particular person, and from that person's phase-related information, it can extract the vital signs. That's what we call Doppler mode. And then another thing we can do, we can use the micro Doppler, which is much more promising for this application. But you can see the radar we use for Doppler mode is basically the cheaper radar. It's called continuous wave radar. But the radar we are using for the synthetic aperture or the micro Doppler mode is a little bit expensive. But what we can do, we can extract the micro Doppler information. We can do the mapping of the reflection coefficient. And from that mapping, we can understand what is the location of that particular subject, and whether he is breathing or whether he's dead. In that way, first responders can go that particular place quickly, and he or she can extract can be saved by the first responders. So how we do the micro Doppler? Just a basic I try to explain. Whenever signal is being captured as an I and Q channel signal, basically we can do the demodulation. As I mentioned, one is called a linear demodulation, as is called arctangent demodulation, and from there we can do the short time Fourier transform. to extract this microdoppler, which basically time frequency plot. And if some people breathing like from, the breathing is a like from 0.2 to or like 0.5 hertz. So in that we can understand like whether it's a activity of walking, whether it's this activity of like breathing, this type of thing we can like understand from this plot. So, but one just a problem from this about in between the two deployment mode, we need a cheaper radar for Doppler mode, but we need a little bit expensive radar for microdoppler. But using the same mode, in the same CW radar, we can also do this type of microdoppler mode is also possible, but we need a little bit more processing in terms of signal processing. So as I said, we can use like unmanned aerial vehicle or drone as a triage assessment tool. As you see, we did this experiment at my lab where I did my PhD. So what we do, we use the drone and then we mount this radar with the drone. So drone is basically acting as a vessel for this particular radar. So radar is basically capturing all related informations and drone is helping to go at different places. So I'll try to show like what we did and what has been done so far and what has not been done. So one of the problem we faced, as I said, like radar is basically capturing the tiny movement of the chest surface. So it's basically capturing the movement of human or movement of the chest surface of the human. But whenever the drone is also moving, the drone will create some extraneous noise. So these two noise will add, and whenever there is undesired phase information added to the radar baseband signal, basically it may be a problematic to extract the reliable vital sign information. So here I'm trying to show like, the respiration signal is represented by cos 4 pi a lambda sine omega naught t, where omega is the fundamental frequency. And when there is a phantom or platform signal, like when the drone itself moves, basically it creates some extraneous noise, and both of these noise will be added. So at that point, it will be hard to extract the reliable vital sign information, and we try to solve this particular problem or particular challenge. And I'll show like what we did and what type of filtering technique we used. So here, our research challenge was like how to compensate this platform motion to extract the reliable vital sign information. So as I said here, the research challenge, I already showed how indoor drone radar-based respiration concept works. So here I already talked about it, but I'm trying to show here when people are breathing, basically radar one is capturing the tiny movement of the chest surface. At the same time, there is a movement of the drone motion and breathing motion is added together. And at that point, like capturing or extracting the vital sign information is a little bit challenging. So what we did, we put another secondary radar. So one is a primary radar, which is capturing the tiny movement of the chest surface, and secondary radar basically capturing the movement of the drone. And then we use the adaptive filtering technique, which basically is a little bit different than other filtering technique where filter coefficient changes with the noise information. So we need both a signal plus noise and noise information, and from there it tries to extract the signal information. So this work we already published in like a conference, and we also have one of the paper related to this work, which is under revision. So we try to compensate this platform motion for extracting reliable vital sign information. So here you can see I'm talking about the adaptive filtering technique. So I'll try to discuss a little bit like the basic how this adaptive filtering works. So you know that when there's a signal, we can do those who are familiar with the signal processing is very simple. We do the digitization, and then in a FFT, we basically can see if there is a sinusoidal signal, we can see just a single peak. Now, just a single peak, and based on that particular signal information, we can design the transfer function of the filter. And using the transfer function, basically, we can extract the reliable information. But what would happen, like when noise itself changes, means the platform motion will be when the drone will go like faster, there will be sometimes noise will be much more higher. When the drone will go slower, there will be less noise. So noise itself is adapting. So what happens is as the noise is changing, basically we need a different kind of filtering, and we are using the adaptive filtering where filter coefficients need to change and needs to adapt to extract the reliable vital sign information. If we use like normal filtering, like bandpass and other filtering, then it will not work. But if we use the adaptive filtering, then it works. And I will show like we not only initially we did some simulation. And before simulation, we did this anechoic chamber experiment where you can see this is a phantom mover which can generate different respiratory pattern. So before going into human study, basically we tried to show, like, let's say this phantom can generate different type of signal, like it can generate sinusoidal signal, it can generate square wave, and different waveform it can generate. And then we try to, so let's say this particular drone is moving, and drone movement and radar movement is being like combined. And when it's being combined, like how to extract the reliable vital sign information. So we try to do this type of testing first, and then we moved into like in a realistic settings experiment. So this was a kind of like control experiment we did. And here I'm again trying to show we use two radar. One is a primary radar, which is basically capturing the breathing motion of the phantom mover, which can generate different types of breathing pattern. And then from that particular information, we are getting like breathing plus drone motion. And then we use another radar, which is basically secondary radar that is capturing the movement of the drone. So then we use this breathing and drone motion as an input for the adaptive filter, and this drone motion is also used as an input for the adaptive filter. And then we try to see like how this performs. So we use different adaptive filtering algorithm. If you look at the literature, there are different like LMS, least mean square, recursive least square. And I'm not going in detail about this filtering technique, just I'm trying to show like how this type of research can be conducted by simulation and other thing we can also do if we don't have the infrastructure to do some experiments. So here I'm trying to show, let's say we generate some breathing mover signal using the phantom mover, and then this is a drone mover, and we add this breathing mover and drone mover. You can see the combined mixture, and we try to see using the adaptive filtering technique here. You can see the blue line is the original signal, and red line shows the reconstructed signal, and they are quite closely perfectly matches, I should say. And then we try to see where we use this is results for RNS filter, which has an order of 32. And its initial covariance estimate was like 0.1. Similarly, we tried this experiment or tried this simulation with a square waveform. Then there was a drone mover noise. We added them together, and then we put them to the adaptive filter and try to see like how this signal can be reconstructed and whether there is a matching with the breathing mover or not. And we found the RLS with a filter coefficient of 32, with the filter order of 32 shows the best result. And initial covariance estimate, we need to put like 0.1 to get the reliable results. And using the same filtering technique, we did this experiment in an anechoic chamber where we used the phantom mover as I showed this experimental scenario here. So we did this experiment in an anechoic chamber. And once we did this experiment in an anechoic chamber, we can still extract the reliable information. You can see the first I'm showing here breather movement, then platform motion. We added them together. This was the breather plus platform, and this was the reconstructed signal using the RLS filter. And then we try to compare the RLS filter results with the other filtering technique that's called LMS filter and other filter. And for comparing, basically, or for comparison, basically, we try to see reconstructed signal FFT and the original signal FFT, and then how much variation occurs. We found that the RLS filter accuracy was like always almost 98% based on our both the simulation and the experimental results. Similarly, for LMS, the accuracy was less, it was like 88%. So you can see the reconstructed RLS, reconstructed LMS, then we took the FFT and tried to see like how different they are. And almost all the time, like this RLS filter like supersedes other filtering techniques. And then once we got confidence about these simulation results and phantom mover results, we started working on like doing some real-time experiment, like when participants are in a seated in a like sleeping position, and we took the drone with the radar, and we did this experiment in a two-way. One, we put the radar with the drone in a static position, and then it starts like flying over that particular subject. And you can see here, when drone is in a static position with the radar, it shows a vital sign that we are getting from the RLS filtering technique, as I mentioned. And now this breathing pattern, what we did the FFT, fast Fourier transform, and from there we can get the vital sign like the breathing rate and heart rate related information. So it's quite accurate, even though participant was like in a seated position, and there was a this is not a controlled environment. What we did before in an anechoic chamber, it's a kind of like a real-time experiment. And then from here, when it's going through the flying path, due to the movement of the drone, you can see there's a little change in the signal, and it's not that much periodic with the previous results. And in the spectrum, if you see, still we can extract like the breathing rate and heart rate related information. So it's a good news that so we can compensate the platform, and we did some initial experiment where participants were in a sedentary position, and we can extract like the reliable information by integrating the radar with the drone. So I think in the literature, if you look at the literature, people didn't do that much apart from this recent work. Like people tried so far how to integrate the radar with the drone, then how to compensate the platform motion, and how to extract the reliable information. So there are a lot of challenges existing with this technology. As I mentioned, one of the challenges is like, that this type of scenarios or this type of experiment was done for one subject, single subject. When there is a two subject presence, let's say in a room environment, let's say there is a router. So when there is a router, basically signal is being reflected from the two participants. So both of the signal will add together, and which will act as a interference and extracting a reliable information from the combined mixtures of these two subjects breathing pattern is still a challenging task. I mean, there are more subject and some object. So how to remove all this clutter and how to remove these combined mixtures of the two subjects' respiration pattern. So these things need to be being investigated. We also published some paper, and some other groups are also working. So still a lot of tasks need to be done to bring this sensor technology for UAV deployment. So now I'll try to show like how different application areas it can work on, or we can work on. Like radar is basically using, as I mentioned, it can use for remote breathing monitoring. It can use for unique identification, like recognizing people from the radar capture respiration pattern. Another thing, I think you are familiar with the Google phone. In the Google phone, you know that like using the hand gesture, you can control button without touching any button. So that has been done in one of the project called Solid. If you write down in Google, you can see that that project is called Solid, and it's now in a real life. So it's no more in a laboratory. It's being used in our Google phone. If you use Google phone, you can see that this radar technology is being used for controlling different buttons of the phone using the radar. And similarly, nowadays, people are also investigating like counting number of people in a room using radar signal, and then how like energy management can be much more efficient. This type of work is also going. And now, as we are passing through COVID situation, we know that COVID is basically respiratory related disorder. We all know about it. So this non-contact sensing technology may have much better role if we can push this, or if we can drive this technology in real life. So you can see that radar or Wi-Fi router in our home environment, if it can track apart from giving a service for communication, if it can track our respiratory pattern, whether we are like sick or other thing. So this can be a potential new area and potential emerging application. Similarly, we can use drone technology in a hospital environment where it can track different respiratory disorders, like whether we can say that some participants or some patients, whether they are like in a normal respiratory pattern, whether there is a respiratory disorder. So all this futuristic project we can work on, and we can drive this technology towards the benefit of humanity. And in conclusion, I would say like so far for UAV or drone-based remote life sensing technology, stationary human subjects can be detected. And as I said, this is the recent progress, and I'm pretty much sure I'm working on this area. So I know like none of them showed, apart from stationary human subjects, none of them shown other results at least in the literature. And different levels of activity can be identified and classified using Doppler sensor. Similarly, radar can discriminate between stationary subject and other movements. And as I said, we need to have a further processing possible for like separating, counting multiple subjects. So we need a new algorithms and single processing algorithm that need to be integrated with this technology. And challenges, as I mentioned, there is a coverage area, like how many drones can be covered and how many radar we are going to use. So all this calculation, whether we are going to integrate any optimization technique, whether machine learning can be integrated. So all this need to be like investigated. And another thing like sensing platform, whether we'll use the camera or whether we'll use radar. If we use both technology, like how to combine both of them, this term is called like sensor fusion. So all these challenges are existing as it is new technology, not that much mature. So it's a good or it's like one of the potential areas that we can work together and we can collaborate. and we can publish a lot of papers, and we can basically drive this technology in a new dimension. So with this, I would like to thank you for your patience.
থ্যাংক ইউ স্যারকে খুব সুন্দর এবং খুব ইনফরমেটিভ একটা ওয়েবিনার কন্ডাক্ট করার জন্য। সো আমরা এখন হচ্ছে ওপেন কোশ্চেন অ্যান্সার সেশন। সো কারো যদি কোনো কোশ্চেন থাকে, আমরা চ্যাটে আপনাদেরকে রিকোয়েস্ট করেছিলাম, সো চ্যাটে আমরা মনে হয় মাত্র একটা কোশ্চেন দেখতে পাচ্ছি। এছাড়া কারো যদি কোনো কোশ্চেন থাকে, কোনো ওয়ারিস থাকে, সেটা যদি স্যারের কাছে করতে চান, তাহলে আমরা এখন হচ্ছে এই মুহূর্তে কোশ্চেনগুলো নিব। সো আমি একটু রিকোয়েস্ট করবো, কারো যদি কোনো কোশ্চেন থাকে হ্যান্ড রেজ করলে আমরা তাকে ফ্লোর দিব, এবং সে যদি কোনো কোশ্চেন করতে চান। আর যদি কোনো কোশ্চেন না থাকে, তাহলে আমরা হচ্ছে যে অলরেডি যে কোশ্চেনটা আসছে, আমার মনে হয় স্যার অলরেডি এইটার অ্যান্সার দিয়ে ফেলেছেন স্যারের প্রেজেন্টেশনে। তাও যদি স্যার একটু ইয়ে করতে চান। আবার মুশিদ প্রশ্ন করেছেন, when the drone flies there will be some vibration, does the vibration has any effect with the signals we receive? মানে সিগন্যাল যেটা রিসিভ করতেছি সেখানে ড্রোনের ভাইব্রেশন বা নয়েজ সিগন্যাল।
Right. So if you look at my slide here, that's a good question, I would say. So if you look at the slide here, so I talked about the platform motion. So there's as we are using the radar and a drone creates some extraneous motion. So we try to solve that problem using adaptive filtering technique. As I said, as I showed some results, initial results, and then some simulation results, experimental results. So using filtering technique is possible to compensate that platform motion, and reliable extraction of vital sign is also possible, that we already demonstrated in our paper. And if you're interested, you can look at this paper, like an adaptive filtering technique for platform motion compensation. We already discussed about the possible solution for this particular challenge.
তো আমরা এই মুহূর্তে চ্যাটে আমাদের আর কাছে কোনো কোশ্চেন নেই। সো কেউ যদি কোনো কোশ্চেন করতে চান, আমি একটু রিকোয়েস্ট করবো হ্যান্ড রেজ করে যদি আপনাদের কোনো কোশ্চেন থাকে স্যারের কাছে, সেই কোশ্চেনটা করতে পারেন। আমরা ওয়েট করছি, যদি কারো কোনো কোশ্চেন থাকে তাহলে আমরা
এখানে দেখতে পাচ্ছি মাহমুদুল হাসান শিশির raised hand.
Assalamu alaikum, sir. Sir, I have a question that this is a research, rescue-based radar system, right, sir?
Right,
then there will be many source of life there in the wild or in the environment when the where the radar and the drone will be operating. Then how it will differentiate the sign of human and other living things?
That's a good question. So let's say you are using some pet like dog and cat and other thing maybe there, right? So you know the breathing rate of human being and the breathing rate of like the dog is different. Similarly, like breathing rate of adult and breathing rate of like a newborn baby is different. So we already know in the literature like what are the range. Like let's say someone is adult and someone is like at a normal condition or normal state, sedentary. So at that point, his or her breathing rate should be within 12 to 20 beats per minute in general. And if someone is like, let's say we are stressed or we have some physiological stress or other thing, then breathing rate will change. Similarly for dog, cat, already people are working on it. That's called like they are trying to develop dog filter, cat filter. So using that filter, you can find this is a respiration rate of dog, this is respiration rate of cat, this is respiration rate of cow, something like that. So there is a differences in the respiratory pattern of the living being. So I think that can be a way to like discriminate between the whether it's a living human being or whether it's a living like a pet. So I think that can be a way. Does that answer your question?
Yes, sir.
So আরো কারো যদি কোনো কোশ্চেন থাকে, if anyone else has any questions, so a video recording, the recording will be available through our YouTube channel. We will publish the recording. So anyone interested to go through the video once again, you can find it in our YouTube page. So Bangladesh Flying Labs YouTube page. So if we don't have any other questions, so we
You can see in the chat box, Nafis Fuad Milad. Nafis, you can ask.
Assalamu alaikum, sir. Sir,
Okay.
if the body is in motion, suppose if the body of the person is in motion, then is it possible to acquire the correct signal of its heart rate or breathing rate?
So I understand your question. So I already showed you here. You see here. So we captured like when people are moving his or her limb and they are like sitting or they are like walking. So you can see when there is a limb movement, there is a much more like if you look at the amplitude, it's different than the normal respiration pattern. And what you can do, we call it like periodicity test. If you look at the periodicity, this is much more periodic than this portion. So doing the periodicity test, you can basically remove the non-periodic part and you can just focus on the periodic part. So in that way, like we can basically discriminate different activity or different limb movement, hand movement, and other things. Is that clear?
Yes, sir. Understood, sir. Thank you.
So আর যদি কারো কোনো কোশ্চেন থাকে
এখানে একটা কোশ্চেন দেখতেছি দিগন্তিকা ঘোষ ইন্ডিয়া স্যার প্লিজ সেন্ড ইউটিউব লিংক
জি সো
ওকে মিশাল ইসলাম অলরেডি শেয়ারড ইট
সো আমার মনে হচ্ছে আমাদের আর কাছে আর কোনো কোশ্চেন নেই সো থ্যাংক ইউ স্যার আমাদের সঙ্গে খুব ইনফরমেটিভ এবং খুবই সুন্দর একটা সেশন শেয়ার করার জন্য আপনাকে অসংখ্য ধন্যবাদ সো আমাদের এই আমি যেটা অলরেডি বললাম আমাদের ইউটিউবে চ্যানেল লিংকটা অলরেডি মিশাল দিয়ে দিয়েছেন চ্যাটে তো ইউটিউবের লিংক ভিডিওটা লিংক মানে ভিডিওটা এখানে আপলোড করা হবে আপনারা সেখান থেকে চাইলে পরবর্তীতে আবার রেকর্ডিংটা দেখে নিতে পারবেন সো আমাদের সঙ্গে জয়েন করার জন্য সকলকে অসংখ্য ধন্যবাদ আমরা আমাদের আজকের সেশনটা এখানে শেষ করছি